These are the notes for the second day for Chapter 20 from the McGraw-Hill chapter on electrochemistry. The Section 2 is labeled batteries. Probably could be called batteries and cells because it deals with both of them. And there is a difference. You need to make sure that you understand what the difference is. This is a cell. If we put two of them in series, lined up one after the other, then that would be a battery. A battery, basically, that term means things that are lined up in a series. Back in World War II, they had batteries of gun emplacements that were lined up along shores to protect a country. So this is a cell, and it'll actually say it on it. If you read it, it'll say something about a cell. And this actually is a battery. So, if you open this up, you'll actually see that there's four little cylinders inside that are separate cells. And when you put cells together in a series, their voltage adds up. So here we have a 9-volt battery. We have four cells inside that total up to 9 volts. In your car, you have a battery. It is a battery, and there are 6 cells inside that total up to a little over 12 volts. Pretty much anything that is over 5 volts, has got to be a battery, because if you look at your reduction potential chart, that the top items like negative 3.05, bottom items a little over 2 positive, and remember the way we figure the voltage made by the cell is the reduced number minus the oxidized, which is usually reduced minus a minus, and that gives you somewhere around 5 volts as your maximum. So if you have something more than 5, chances are it probably is more than one cell put together in a series. That's how you add up the voltage. So we're going to talk about batteries and cells. Battery is a group of cells that are put in series to total up a voltage. Dry cells. So we're going to talk about just a generic dry cell, not alkaline. I know they mention alkaline. They talk about the little coin type batteries or cells that you might have in a watch or a calculator. We're going to focus on the just a standard D cell basically, and I want you to know the cathode and the anode, and at least the black mix or the inside paste that surrounds the cathode. On your notes, you'll see that there's a carbon or a graphite cathode in the center, and it's more of a conductor in these cells than anything else, but it is considered the cathode. The outside on a standard cell is a zinc can, and that zinc can is the anode. And there's a solution near the zinc, and there's a solution on the inside near the graphite, and they're separated by a paper porous layer that operates just like the porous cup that we're going to use in our lab when we build our cell. The black mix on the inside is manganese dioxide. That is the paste that surrounds the cathode, and then there's a porous layer that, on this picture up here separates the green from the black, or the outside layer from the inside layer, just like your porous cup. So primary and secondary. To just cut to the chase here, a primary battery is one that you use and recycle or use and dispose. A secondary battery is any battery that is rechargeable. In other words, it's the secondary source of the electricity. It started in your socket, your wall socket. You recharge the battery, and then you use the electricity. So it's the second source. The original source was the wall socket. Secondary means recycled. Lead acid storage battery. So this is the type of battery that you have in your vehicle or in your parents' vehicle, or the 12-volt battery that you would find in a car or truck. I want you to know the charging and discharging reactions. So I've laid them out right here on your notes, and they're not that hard. Obviously, Anybody could learn this if you put some time in, and I will ask you a question on the quiz and on the test about it, so you should be able to write this reaction and tell me what's the anode, cathode, electrode. Well, it's fairly easy because it's a lead cell battery. So what do you think might be in a lead cell battery? Well, lead. And it's lead for the anode, lead oxide, actually lead 4 oxide for the cathode, and sulfuric acid for the electrolyte. And there's an easy way to remember this because the first substance, lead, has 1 capital letter. The second one, lead 4 oxide, has 2 capital letters. And the third one has 3. So 1, 2, 3, A, C, E. 1, 2, 3, anode, cathode, electrolyte. There you go. Easy way to remember the equation and your anode, cathode, and electrolyte. And this is a little more complicated than a standard double replacement, but basically the lead, if you can remember this, the lead switches over with the H on sulfuric acid and we get lead sulfate, and the hydrogen switches over with the oxygen to give you H2O, water. And it's a little more complicated than that, but that's the easy way to remember. And over here at the end, it's kind of off the screen, there is a little lightning bolt which tells you that electricity is also produced. This is the discharge. The recharge is just starting on the right, going to the left. Products are reactants, reactants are products. They're just 180-degree flip. Lithium cells. Main point we make here is that these are popular because lithium has a minus 3.05 reduction value, and that gives you a maximum voltage. On the small devices, we can't have large batteries, so we make a cell that produces a large amount of voltage by itself, and lithium gives you that ability. It's because it's got such a high value. Remember, the potential of the cell is the reduced voltage minus the oxidized voltage. So if those numbers are wider apart, you produce more volts. Important point about lithium. And you've probably heard of lithium-ion batteries and some other types that most of them rechargeable batteries. Fuel cell is just that. And when it was invented, it was actually called a gas battery because people put in a liquid and it powered the battery, just like back in that day, we started with electric cars, and somewhere along the way, they made a choice, and good or bad, they made a choice towards going with gas. And so some of the first cars were electric, and maybe even used a fuel cell like this. But the reason it's called a fuel cell is you don't recharge it with electricity. You drain the fluid, put new fluid in, boom, it's ready to go again. So you really just put fuel in it that drives the cell until it's used up, and then you drain it, put new fuel in, and move on. Hydrogen fuel cells are the most popular. They were developed in the space race and used in the space shuttle and in the space station. So they use rechargeable batteries, they use fuel cells, and they use solar cells. Corrosion. So corrosion we kind of covered in the last chapter. We'll mention it again. Corrosion is a general term for the oxidation of metals, specifically iron rusts. Other metals have like silver tarnishes and copper tarnishes, iron rust, but in general we call it corrosion. So this is kind of like vehicle is a general term, and you could talk about red 2015 Lamborghini for a specific term. Corrosion can be slowed by painting or by coating, and there are some other things we can do too that are kind of creative. When we coat with zinc, we call this galvanization, and the little powdery gray nails that you use when you hammer siding into a house, or the roofs that possibly we see one over here, tin roof, those are either coated with tin or coated with zinc, because it is resistant to corrosion. Another way that we can cause or save metal from corroding, especially around saltwater areas, keep in mind, why do things corrode in saltwater? Well, it's electrons moving. If you remember the demo we did where we had the light bulb in the with the 2 conductors in fresh water, just pure water, it didn't conduct. I poured in salt, it went bright. The reason it does that is that water is a molecular compound and doesn't conduct electricity when it's pure. When we put salt in, it conducts a lot better. Well, how better to speed up oxidation and reduction than to put salt water there to speed the electrons in their movement. So oxygen, water, salt water in particular, speeds up corrosion. So around the ocean and up north where they put salt on the roads in order to help you keep from slip sliding around on your car, where all that salt is, it's really a big deal to try to keep corrosion from happening. One way that they do on Navy vessels, I'm familiar with those, and also on a lot of other vessels, is they put a piece of sacrificial metal on the side of the ship. And what this does, just like the term suggests, is that we sacrifice that metal to save the other. Well, you get something high on your reduction list, the negative reduction, which means it's highly oxidized, and the electrons, it's kind of like an electron magnet. It pulls the electrons that are lost by that metal, and the corrosion occurs on that metal. Well, after time passes, we unbolt that piece that's left that's all corroded and in bad shape, throw it away or recycle it, and we put a new piece in. The iron or the steel in the hull doesn't corrode because the electrons have all been funneled through this sacrificial metal to oxidize. So that is an important way and you know, kind of a creative way to help keep iron ships from rusting. So, electrolytic cells, electrolytic processes. Finish up with this. This is section 3 in the chapter. And I will want you to be able to draw a electroplating cell, which is electrolytic process, electrolytic cell. And you need to be able to draw that from scratch if I give you what metal it is that you're going to be plating with. So some things that are kind of opposite of a voltaic cell, but if you know your voltaic cell well, this won't be that hard. I will be asking you too on the quiz of the test about what are some types of processes that are electrolytic, and electroplating and electrolysis are two of the main ones. Electrolysis gives us a way to split a compound into its parts. Something that's very polar, like water, can be split into H and O, and we'll have an example of that in the classroom. And you know, we've already seen that back in our chapter on chemical reactions during that lab. The second type of processes that are very important, that are electrolytic, are plating. Plating processes are electrolytic because we're putting energy in to see a chemical change. Remember, that's what electrolytic processes are, putting electricity in to see a chemical change, as opposed to voltaic, which are a chemical change that makes volts. So we're going to talk about the electrolytic cell and electroplating, and it gives you the steps. This is how you draw your electrolytic cell, your plating cell, and you need to know these steps. Go through and do a few of them. Once you've done them, they're not that hard. It's a matter of you putting the time in, and if you do it, you can draw the cell. You will be doing one on the test for sure, possibly on the quiz. So here's how we do that. We're going to start out by drawing a battery, because remember, there's a battery on electrolytic cells, because that's what they are. They are electricity making chemical change. So we've got a plus and a minus pole. We hang the wires down from that. Let's say we put this up on a shelf up here so it's up, not just floating in the air. And then we have one container, not like our voltaic cells where we have two half reactions in two separate containers. Here we have one container, and we're going to plate in silver. So on the positive terminal, I'm going to put a chunk of silver, pure silver. And on the negative, let's say we're going to plate a spoon here, okay? So, and it's an iron spoon, just so we know what that's made out of. So, there we go. The item we're going to plate is hung down on the minus, and the item that we're plating with, the silver, pure silver, is on the plus. We're going to be plating with silver, so we need a silver solution. I'm just going to call it AgNO3. Okay? So, remember now that electrolytic processes put energy in instead of taking them out, so we're reversing the direction. We also reverse the charge of the anode and the cathode. Okay, so remember on the voltaic cell, cathode was plus. The T for cathode looks like a plus. Well, now the cathode is going to be switched to the minus. So find the minus, write cathode and reduced. Remember, red cat always stays together. Those are paired no matter what kind of cell. And anode and oxidized are always together. And remember, we remember that by anox, chase the red cat. So an and ox, anode and oxidized, always together. This time, they're on the positive pole. Well, now we know that the reduced side is over here. What's happening on the reduced side? Well, we're reducing silver. Both reactions are going to be with the plated metal. So the reduction would be silver 1 plus. We know it's 1 plus because it's in 1b. Plus 1 electron minus yields Ag, the element, which is 0 charge. The half reactions have to be balanced for charge. 1 plus, 1 minus, that's 0. Silver as an element or an atom is 0 also. The oxidized. So on the oxidized, silver is losing an electron. So we go from silver, the element, to silver, the ion, Ag plus, plus 1 electron minus. So what is it that's really happening in this process now? Because I want you to understand what's happening and what makes it plate. So over here, the silver, we want the silver to jump off into the solution as Ag plus, and then Ag plus be attracted to the negatives over here and turn into silver again. We want the silver to basically jump over on the spoon. How do we make Ag turn into Ag plus, which is part of this solution? Well, we have to oxidize. How do we do that? We take electrons away. How better to take electrons away than attach it to a plus? What are electrons going to do when they see that plus up there? Opposites attract. Electrons race up there to the plus. They leave the silver, and when they leave Ag, it turns it into Ag plus. So this Ag turns into Ag plus out here in the solution. Now we want the Ag plus to jump onto the spoon. How better to attract the plus than with minuses? So we hook that to the minus pole, and that makes electrons go into the spoon, and when the plus attracts to the minuses, now the reduction takes place. Ag plus adds an electron, and it turns into Ag, the element. And the silver's trapped. It's now plated on the spoon. And that would be how plating takes place. Go through this enough times to where you could actually sketch one of these. You'll be sketching one possibly on the quiz and definitely on the test. So that finishes up most of the chapter. We're going to have a few loose ends that we do in the third PowerPoint and the third video. But beyond that, work hard, work on your review, and come in tutorials if you need it or rewind this video. Good luck.